Thanks so much for the introduction, Joanna. A pleasure is mine, actually. Thanks so much for the invitation. I'm very excited to be here and talk about the work that we do in the lab. As Joanna mentioned, I started my work in 2019, one semester before COVID, good or bad, in UT Austin. And started my lab, Arts Lab, Advanced Robotic Technologies for Surgery. The idea is that developing technologies, both hardware, software, even like biomechanics, anything that can help clinicians and at the end of the day with patients. And I call it surgineering or engineering of the surgery, what we do. Let's just define surgineering. I really love this basically word. And that's my definition out of it. Before starting my job, I was thinking actually that any technology we develop from engineering perspective for clinicians are basically the chain of these three blocks. Originally, this picture was made by Dr. Taylor in Hopkins. He's the father of actually surgical robotics. Literally has invented the field. So I took it from one of his courses that I took. And it makes sense. So whenever you are developing any technology, you have basically technologies you are building, any type, hardware, software, and you have a physician directly interacting with it. And then you have a bunch of information coming from sensors, imaging modalities, anything that you are using. So with that, I came up with this sentence. So surgineering is the design for the surgeon and with them. What's the meaning of that? Our end users are surgeons. So we need to build something that they are going to use. But to make sure that they are using it, you need to make sure that you are doing this with them. Because at the end of the day, if you forget that with, you're making something in the lab as an engineer. They start using it in 10 seconds, then they trash it. So as I started my job, I really like commercialization mindset in this field. I came up with another constraint here. So to make sure that basically what you're building, that surgeons like, you developed it together, you want to make sure that you are having other constraints satisfied. What are those? FDA, commercialization pathway. You need to know who is the end user. If you're building something even pretty cool, helping patients and surgeons, at the end of the day, maybe no hospital wants it. You need to know actually who is buying these stuffs for, basically from suppliers for clinicians, and I started thinking about the last term. So we worked with the clinicians to obtain a clinically viable medical goal, which is meaning that satisfying all the constraints I have put over there. So I'm showing some basically examples today that hopefully we have satisfied these guidelines. But before that, I show always in my talks this basically plot from this paper. It's 2012, I really like it. X-axis is the years that major milestones in surgery has happened, from open surgery to minimally invasive surgery to robotic surgery. So if you compare open surgery and minimally invasive surgery, the difference is that the two sides of human beings in this loop, which one is basically satisfied? Open surgery, poor patients having a big injury and incision, to give access to the surgeons digging into their body to do something to help them. So it's good for surgeon's perspective, bad from patient's perspective. Then they develop this idea of minimally invasive surgery. In minimally invasive surgery, patient is happy because incisions are very small. They can get back to normal life faster. But for surgeons, this means that they have lost the direct access to the body and the tools are rigid, so there are a lot of complications. So to fix that, 1990, Intuitive Surgical came in and introduced Da Vinci robot that actually to make both sides happy. So they are sitting behind a very fancy system. They have a 3D view, they have access, and then everything is precise. Still, they are passing through a tiny hole. So patient doesn't have a major incision. But this is in the past. Many papers you have seen over there, and there are a lot of commercialization, as you know. They do more than 2,000 surgeries per year across the board. But the major milestones in our field is building flexible robots to give more access to clinicians in a minimally invasive way. With that, they started the field of continuum robots or doing even procedures with no incision, going through the natural orifices of the body or natural orifice transluminal endoscopic surgery or node surgery. So to do that, we need flexible devices that can go through the hole, and then they can navigate through the complex anatomy to the procedure. And then we have two companies actually already have a product into the market, FDA approved. So this is the bronchoscopy catheter. The other one is single port Da Vinci robot, like coming in from one port and open up, doing a snaking motions and do the surgery. But if you look at the whole products and research, Most of these surgical devices commercialized only are working on soft tissue-related intervention. You cannot find any robot for hard tissue-related surgeries. The next milestone, which is these days everyone is trying to work on, is surgical autonomy, basically bringing autonomy in surgery. But autonomy in surgery is not new. In orthopedics, they have done it actually in 1990 with that company on top. They call it Robotic. Why it's easy? Because it's literally machining. If you pre-plan it, if it's like that, you go to the machine shop, you plan it, and then you cut the tissue. But it becomes very challenging when you're talking about the deformable tissue. This is an unknown property, viscoelastic, meaning that you touch it, the property changing. It's super uncertain. But to do autonomy, people are focusing on this mainly rather than orthopedics. So with that, if you put everything in this chart, if your x-axis is dexterity, you're making flexible robots, and y-axis is the space of autonomy. You look at these 4 quadrants for open minimally invasive surgery, traditional one. There is no basically dexterous tools. There is no dexterity or autonomy in it. But if you go to the top left, orthopedics, neurosurgery, autonomy, in terms of autonomy, we are high. It's machining. But in terms of dexterity, flexible tools, there is literally no reliable tool that's a robot that can interact with the hard tissue. The issue is that your body is compliant, the body is hard, so failing, buckling is happening. Soft tissue is exactly opposite. Autonomy, they are bad, but in terms of dexterity, they are in a good state. So with my lab, we try to be on top right, building intelligent algorithms, hardware sensors that are soft and intelligent and dexterous, depending on the technology. With that, I have 4 main projects in my lab, luckily funded. But they are ending, actually, the funding. God knows what's going to happen for the next years. But started with the top left one. It's a neurosurgical procedure, spinal fixation with a steerable drilling technology and flexible implant. Then the second funding I got was for basically building a new sensor, robotic system for diagnosis of cancer in GI tract, specifically colon cancer. My sci-fi project, top right, I call it sci-fi, because 3 years ago I had zero knowledge about bioprinting. What is bioprinting? And I learned about it. I wrote this basically proposal. What if we use robots to directly print tissues and organs on the lost basically muscle of the bone? They call it in vivo robotic bioprinting. I have also another area of interest here is basically surgical autonomy. But in this case, I want to model human brain into the loop to do surgical autonomy, because to me, that's the main thing that is unmodeled. But today, hopefully, I can basically talk about these 3 projects. I have a lot of slides. I do my best. So let's start with orthopedics. I always put these slides. I love it. Top row is the Roman surgical tools they use for orthopedics. Bottom one is what we use right now in the operating room. I love the first row because it's more artistic even. I don't see any change even here. And then another one, left side are the tools that they are using in orthopedics actually. Operating room, right side is carpentry tools. Pretty much the same thing. It's just more expensive, 10 times more expensive because it needs to be sterilized, made of titanium, so on and so forth. So that's the state of orthopedic surgery. And with those tools, one of the very common surgical procedures actually surgeons are doing in the spinal column, excuse me, is a spinal fixation. What is a spinal fixation? Different problems happening to the spine, from basically fractures to disc degeneration, or even deformity on the spine. What they do, they use a surgical drill, go through these areas of the bone that we call it pedicle. And this anatomy is very complex. Try to avoid nerves. This is basically this hole, a spinal cord passing through this hole, and there are a lot of vasculature, so it's a very sensitive organ, very basically curved. What they do, they try to very precisely go through the pedicle channel and then make a tunnel and then put 2 screws, rigid screws, into these holes. And what they do, to avoid pain, they lock different levels of vertebra together. Why they do it? To make sure that the body is fixed and they are not pinching on the nerves. So the pain is gone, and then the patient can come back to the basically their life. But the issue is that if the bone is osteoporotic, what's osteoporotic? Means that the bone density is lower than what it's supposed to be. And if the bone is osteoporotic, and you only have one basically canal, accessible canal with rigid tools that you have, and let's say this part of your bone is osteoporotic and you are placing a screw inside that region, what happens? It fails. You're mechanical engineers, I guess, most of us. You're fixating the screw into a softer part. So what happens if the load comes in? Loosening happens, or worse than that, the screw pull-out is happening. And the statistic shows actually eventually all the fixation on osteoporotic patients is failing. Why? Because poor surgeons, they don't have any other tools. At best, they can just place it perfectly without pinching on the nerves, compromising nerves at here. But we know that that's not an optimal solution. Then I wrote this proposal, what if we make this fancy neurosurgical system image-guided that try to understand which part of the bone has harder tissue, which is less osteoporotic, let's say, curve into that part and implant and fixate in those regions. So, and this project has different perspectives. From building the robot, a steerable drilling robot, to shape sensing, to image guidance, to biomechanics and implant development, there were like different aspects on it. So our solution to that was this basically framework. It has different modules. First one is that biomechanics aware planning. So let's say I have the ability to curve in and create curved tunnels anywhere I want inside the basically vertebrae. So what is the best one in terms of if I implant my screw inside, if the load comes in, this would be the most stable fixation for me. So let's say we plan that and we do it through biomechanics. I will talk about it. Then I command the desired trajectory. I need a robotic system perfectly going and executing that. Then this trajectory is not straight. This is curved. So I cannot use a rigid screw. So I need to make a flexible implant. So that would be this thing. And then there is a bunch of FDA-approved guidelines to follow that, to say that, okay, now I have a new implant, new device. I will talk about different modules one by one. So let's talk about biomechanics module. What is that? So CT scans, I think you're familiar with. Instead of CT scan, we are using quantitative CT scan. What is that? You're just putting just this phantom under the body of the patient. You take the CT, then you can map the bone density. You can know, for instance, this part is osteoporotic, but these areas are safe. So this now gives me the ability to plan. So to plan that, in this case, what we did, we just had different trajectories, feasible trajectories, avoiding that area that is feasible to drill as well, and then running a biomechanical analysis, and then with different metrics of a stress and a strain, picking actually this trajectory is the best for me to run. So now I have a biomechanics aware planning module. Now I have it. Next step is that I did this, how I'm going to execute that. So with that, what is the motivation? Motivation is that rather than using a rigid drill bit shown on top, which is just a straight trajectory because of the rigidity of the line and then complex anatomy, can I make basically a drilling system that can curve in wherever I want to put it? So before starting my job, I worked in Hopkins in this kind of drilling system, tendon-driven continuum robots. And I started with that. It was a 19-hole tube with a bunch of notches around. You pull the tendons and it has sensors on it. We were somehow successful, but the issue was that the body is that compliant when you are interacting with hard tissue. There was a lot of vibration. It was breaking at some point. And to avoid breaking, I was basically slowing down the whole process. Something that surgeons do in 30 seconds, we were doing it in 10 minutes. Remember surgineering? That was horrible. No surgeon is going to go and use this. So I'm going to go and take a coffee and come back. Let's see the robot has made that tunnel or not. So with that, we say, I don't want to do this. I want to look for basically another trajectory. And to do this, and COVID hit, we started my job and I said, okay, there is no lab. What we should do, we went back to modeling. Let's model all continuum robots, soft robots, which are tendon-driven. We started developing a bunch of mathematical models that you are tendon-driven or you want to model friction too, which is horrible. It's very hard because there are a number of unknowns or more than knowns of the problem. So we did a bunch of basically models, published this, even like with notch, without notch, tendon is basically wrapped around, or you have multiple tendon. I'm not going to talk about it today. There's a huge mass. So today I want to say we did all of this and then ended up with this design. I think you're familiar maybe with concentric tube robots. So what is concentric tube robots? There are a bunch of pre-shaped 19-hole tubes. They're nitinol tubes. You heat treat them with a specific curvature, and either of them have 2 degrees of freedom. You can insert them and you can rotate them. It's very well established, 20 years. Dr. Webster, Pierre Dupont, they are the gods of actually CTRs. But what they have done, these robots, they are so tiny. They are used for mainly soft tissue related interventions, and actually they are avoiding contact with hard tissue because they're so tiny. As soon as they touch, they bend, the whole kinematics is gone. So they can rely on it. But what we wanted to, inspired by this technology, make a basically concentric tube, a steerable drilling robot that can interact with the hard tissue. So what we did, we started basically adapting this technology and then made our very first 1 degree of freedom concentric tube steering drilling robot. What is that? It's just a bunch of pre-curved nitinol tube constrained into a stainless steel rigid tube. It's basically a guiding cannula for you coming from the biomechanics module. Remember I said I want this trajectory, so I heat treated to that shape. And inside that, I put my flexible instrument. It's a torque coil, laser welded to the shaved drill bit. So now I have a flexible drill bit rather than rigid drill bit. Now I have a motor here rotating my drill bit. I have another degree of freedom pushing this tube in. Simple one-off. We made it, and then we tested on different cases to create, I call it a C shape. Even we were very excited about this, creating a U-shaped tunnel. Basically, you go from one end, you can drill, and then come back from the other end. But this was a one-off, meaning that you had one insertion, one tube, one curved tube to do it. Then we said, why not? We have one tube. Yeah.
With your 1 degree of freedom, when you're going in bone, with like the uncertainty and the not, homogeneous, how much uncertainty did you have in terms of like where you
trajectory? Yeah. So it's a very good question. Actually, the thing is that the stiffness of this tube is by far more than the anatomy that you have. So you have that issue when the body is more compliant than the environment, so that guides your tube. The tubes are still stiffer than the body, so you're following actually the trajectory of the tube. And all the thing we did, the error was less than, let's say, 1 millimeter. And then we spend a lot of time, because it's a good question, because the challenge is that you want to be compliant and you want to be stiff to avoid buckling. So the trick is, what's the size of tube that you are picking? If the wall thickness is very thick, you cannot bend them. They shatter during heat treating. If it's very thin, you are going to basically deflect, and that issue is happening. So we did a lot of testing, different manufacturers, and came up with this. Yeah. So 1 degree of freedom, and then what we did, we said, I have one tube, but what if I change my actuation? Now I can rotate that tube too. So 2-DOF. Cool thing happens, you go in, similar to machining with lathe that you are just limited to Cartesian movement. Now you assume you go in, you rotate. You can create cavities or cut cavities like this. Why this is cool? Minimally invasively, you can go into the bone, remove a cavity and come back. Right now, they cannot do this. They need to completely remove that level of vertebra and put an implant inside. So minimally invasive cavity drilling, a spiral drilling was one thing. Then we said, what if we put 2 tubes inside each other? Now we can drill actually an S-shaped trajectory, both planar and out of plane. The cool thing is that you can drill in one plane and then come up, rotate your tube. So you do out of plane. It has applications in actually pelvis, one of the most complex anatomies we have. There are a lot of curvatures, a lot of vasculatures and nerves here. Right now they are using rigid drill bits this big and screws this big. Putting, I don't know how they are doing it, inside this actually anatomy. The issue is that the thickness is changing too. It's like 2 millimeter becomes 5 millimeter, then become 2 millimeter. We said, what if you do this, and then you basically change the procedure? Then we said, okay, I'm a roboticist. That was like a tabletop thing. Let's put it on the robot and do a robot-assisted procedure. Admittance control, and the user is involved. Let's do admittance. And here we are showing actually, these are the desired trajectory, how much error that we are getting if you repeat the task. It's pretty repeatable. And the basically cross-section of cuts are very robust because the body is robust. It's not basically vibrating. So we did all of this. That was a basic robot involved. Then surgeons love to be in the loop. They love that haptic feeling. If it's a bone is high quality or low quality, it basically presented this user study. If you make a handle and the user helps with pushing the robot in drilling, all the testing to basically see typical approaches, NASA TLX in terms of time and other things, we realized actually I don't like those metrics. We need more because every person is different, every user is different. You cannot find a pattern. Then we said, okay, autonomy, we want to do autonomy, and then why not making the whole thing autonomously? So we did like basically planning in the CT scan. Let's say I have a planning, I know where the patient is, I do all the registration, hand-eye calibration, and basically human to robot calibration and everything. And let's do this. For the first time, we made these phantoms of vertebra. Outside was basically plastic, inside was this sawbone, basically phantom simulating different level of stiffness. And then basically the robot, in the beginning, user introduces the thing, and then under the supervision of the basically user, you push the button, it goes in and makes basically all of these cuts as you are planning. So basically, we did biomechanics. We have a robot that can execute. Then the next question is that you need a flexible implant. Rigid implants cannot be inside. So we started additively manufacturing our semi-rigid, semi-flexible pedicle screws with titanium and stainless steel. So this is a cannulated screw, and then it's basically self-tapping, meaning that it can actually create its own tap. You can basically push it in inside a drilled trajectory, put it in, it can create actually its own threads and follow the track. So it's morphable, we call it, and it can basically tap itself. But what is the main characteristic left? So if there was a neurosurgeon here, orthopedic surgeon, the hand was raising, how about the stability? Because you're doing a surgery, the whole idea is it needs to be stiff enough. So we follow FDA-approved test. One of the tests is pull-out test. Basically, they put the screw inside the sawbone, these phantoms, different levels of stiffness. They call it PCF. So 5 and 10 is like osteoporotic, 15, 20, up to 30, they are normal bones. And you pull the screw. And what they do, they basically, plot displacement versus the forces you are measuring with your basically MTS instrument that you have. But what we see here, if you see here the pink, this plot is a normal rigid screw. What happens? You pull it, that's a rigid body. You pull it, the whole body moves together, and then at one point it fails. But what we have a sort of a spring. We have a elasticity in our screws actually showing is pretty good, meaning that instead of failing at one point, it resists to the failure and then fails, and you can see it here. This basically our screw is opening up to some points, resisting because of that elastic nature, and then fails. So we did a lot of, here you see, we are doing a lot of basically computer vision and imaging analysis to analyze actually how these threads are moving over time, which is this. And this is helping us these days to optimize the design of basic threads. Since I'm 3D printing, there is no limit into be like symmetric exactly as is. We can change the thread geometry to make sure that we are delaying that failure. That's what we are doing. So now I have a robot, I have a plan, I have a screw. We introduce a spatial spinal fixation. So normal spinal fixation, you are limited to one plane and then one line. But now we can anchor our screw wherever we want. And we call it a spatial spinal fixation. Here is basically showing this is one set of screws in different planes. Front view seems that they are actually coming to one plane, but if you look at the other views, you will see that actually they are bending in different directions. And also we introduced this concept. To me, this is the most stable theoretically fixation that we call it a bridging fixation. You have one screw flexible coming in, the other one, and they are mating at the middle. So in this case, it's almost impossible to pull out because if this one wants to pull out, the other one doesn't let it go. And in terms of biomechanics, you're creating a bridge at the middle here that distributes the load, so minimizes the risk of failure as well. So we showed here actually you can make the tunnel with the robot and then place this too. So this is relatively actually recent, just accepted in IRA's conference. Was the first time we have our robot, we have our phantom, we are basically a CT-STR and then X-ray matched all together. Through the process, we were actually taking pictures. And everything was registered. So we had the anatomy, The clinician is 4-step going in, touching the entry points of the body, or like the phantom in this case, pedicles. With the right orientation, you're commanding the robot was going hit there, making a pilot hole straight, and then curving in. You're just taking all the basically images with the X-ray. Then we said, let's do our very first cadaver studies. That was our second. The first one was actually in year 2 or 3 of the project. It's a whole failure, but we learned a lot. It came back, it's a human cadaveric actually bone. 4-step procedure that I showed in the lab, we tested on a cadaver. Basically, it was a lot of learning, because if you have worked with cadaver, it's horrible. It's very hard. You want to make sure that nothing touches the robot, everything is basically fine. And it's a real human for the first time. It's not just one vertebra that you have. So poor students. So 2 weeks we had that basically lab. And then they spent like 13 days over there preparing everything. And then to do the test, they were drilling, everything was failing, coming back to the lab and then doing it again. But it was I call it 60% success. Because we realized there are a lot of failure in our mechanism of drilling. We came back, reinforced that hopefully soon in fall we are going to go back and do the procedure. So shape sensing, we use, if you know, like optical fibers people use a lot. Fiber Bragg grating, FPG optical fibers. These are basically shape sensors, fibers you can place into your devices, flexible devices, and they measure basically a strain through optics. Why these are cool? Because they are small. You can put it into your devices. They are biocompatible. And you can embed them into your devices. With fiber Bragg grating, there are a bunch of nodes, gratings, that those are your sensing, discrete points. But here we are using OFDR, which is optical frequency domain reflectometry, basically physics used in these fibers. What they give you a continuous measurement across the fiber. So with FPGs, typically you need a lot of nodes, sensing measurements to see what you have, and then you need to have complicated actually fabrication, very fancy tools, expensive. Here we just use a flat nitinol wire and one fiber. Placed it to our robot during drilling to give us basically real-time strain measurements after calibration. This is X-ray view. This is basically what we are reconstructing with our optical fiber through the drilling. Is one of the curvatures, what we are showing actually what's happening here. What we did here, I forgot to say, we are using actually what we are showing, which is interesting, Joanna. We are not even integrating it, attaching it to the robot. We are that's actually loose into the body. Even if it's not integrated, we are passing it through our instrument channel. It's playing inside, it's giving a reliable information. So, I want to completely switch to a totally different domain. So we talk about the spine, hard tissue. Now I want to talk about relatively soft tissue, basically cancer diagnosis in a GI tract, but the focus is mainly on endoscopy, colonoscopy. So if you're familiar with endoscope, colonoscope, what are those? It's an archaic devices built in 1950, long tubes with an optical fiber or camera in the end. And clinicians are using these control handles to control the bending. They can bend left and right, up and down, and the insertion is basically controlled with one hand. But look at here, you have 2 DUF, and then one insertion, and clinician has 2 hands. So it's already unintuitive to be used. And another challenge is that they don't see the body of the device inside the body. What they see is this view, which is camera view, and they are looking for very sensitive thing, polyps and tumors, to detect this person has basically cancer or not. Another issue is that there is no sense of touch here, which is very important for clinicians. And what is cool is that, cool in terms of engineering, so if the polyp grows, it becomes stiffer and stiffer. So if you can have the sense of touch, you can know actually this is normal polyp, what stage of polyp or cancer you are at, one thing. Second thing which is important, I have it in this slide, is that different types of cancers, like let's say you have basic cancer in colon or GI area, they have different types and they have different textures. So if you have type 1, type 2, type 3, literature shows that their basically texture is different. But those textures, typically you cannot capture them with normal cameras. So issues of handling steerability. Second one is that no sense of touch. Third one is that camera always gets occluded. Doesn't matter if it's a mobile robot or a endoscope inside the body, they are getting occluded. So with that, we said, what if we can modify our current tools and create a sort of balloon with a sense of touch and complementary AI that can help. Actually, there is something over there with this level of basically sensitivity, and then just guess. And then robotizing, rather than building the whole thing, let's robotize the existing colonoscope, make it easy for them to do the process. So with that, we have this framework with 3 solutions. One is the sensing module, which is a balloon. Second one is that a simple, basically, gripper that robotizes the existing colonoscope with a nice interface. And third one, we have a full module of AI, synthetically creating images and then doing classification and so on and so forth with Gen AI. So first time I saw this vision-based tactile sensor was actually during the COVID 20, one of the IRAS conferences. I got lucky invited into a workshop, gave a talk, and there was one person, Dr. Wenjun Yuan. She's now in actually University of Illinois. She had built during her PhD this actually tactile sensor. Super smart actually design, very simple, super smart. You have a camera and you have a gel layer which is deformable. So any object touches the gel layer, deforms that. And if you have a camera underneath, you can basically see the texture of that object. That's simple. So basically you see over there. And with that, what we did, we just said, okay, let's make what they have. And she was actually nice enough sending one of the sensors to my lab, and we started inverse engineering. I mean, mechanical engineering said, okay, let's just build them ourselves. So we made this. And if you see this, these are different size, real size of polyps, different classes. They have different textures. This is the sensors we got from them. And then we modified their structure. They got a super sensitive, high quality, high res over there. We are talking about 10 millimeter by 10 millimeter. We can get up to 20 micron resolution on the texture. Now imagine you can basically push this to the body and see the texture. But the issue is that it's made of rigid structure and is that big. So it took us 2 years to say, what if instead of that rigid structure, we make an inflatable balloon and make a tactile sensing layer on top of it and have the camera and other thing and make this basically this ring that can be integrated with the existing colonoscopes at the end or distal end of the robot. Still you have your colonoscope. Clinicians love what they are using, but we are augmenting what they have. So, and they love balloons. If you talk to them, they use balloons everywhere. From cardiovascular to other indication, they use balloons. So we did this. We attached it to a colonoscope. Half of my lab, we buy stuff from eBay. So we bought a used colonoscope and imaging unit, and then we are basically showing how we manipulate that. But what is cool is that sensitive. Every Lego block, with the tiny font they write Lego on top of it, we can capture even that tiny font here. So that was like a first generation which had a localized sensing area. But if you are in the colon, you want to have a 360 view of the whole balloon. So then we made this. You see the whole thing is gray. Gray means that it's a sensing area. So we made this fully inflatable balloon with like 360 sensing. And here he is showing actually he's touching different things. The last thing is actually his fingerprint even, barely touching it. You want it to be that sensitive when you are inside the body because this is tumor. If you push a lot, you might break the tumors and cells goes in. Instead of helping patient, unfortunately, bad thing happens. So we did the sensor, and then we said, I want to robotize the colonoscope rather than building the whole thing. Just made a simple gripper inspired by the basically collets that we have in a handheld drill. Simply you have a drill bit, you just rotate it, and then you just close the thing. Here we said, what if we have 2 nested collets inside each other? Each of them going in and gripping on the control handles that I was showing you. Now I have 2 simple motors. A very simple mechanism like this can pretty much be controlled by a joystick. So then with that, if I attach my balloon at the end effector, I can control left and right, up and down, and insertion with this mechanism. Push a button, it inflates when needed, and deflate it, and then get the images over here, and then pass it to the AI that we have. So we did all of that. Then my student in January, he said, I want to go to India. I said, there is one condition. You take your laptop with that joystick. We are going to do a remote colonoscopy from India to Austin. So he was like poor, he was like awake in 1 a.m. We were like at 10 a.m. here. And if you see, there are like different things. There is an IP of IIT India. Apparently they are living in the campus. So we were controlling this with a simple, basically, device. So colonoscope was in Austin. He had just joystick and his laptop. You're working on a network. We had about like 500 millisecond delay. For this application, doesn't matter. Everything is slow. So and then we could see everything. So we just did a very basic teleoperation. Then I got lucky. I had randomly someone from Japan reached out to me. I have a student wants to visit because his wife is in Austin. I said, yeah, why not? Let's work together. Just started building this nice, actually, soft robot that can move inside constrained area like a pipe by a mechanism which is vibration and inflation deflation. So the cool thing is that the robot, inspired by pufferfish, we called it honestly after we made it, because it has a spikes and it's made of silicone, and it has a motor, vibration motor with the eccentric mass. As it rotates, it creates vibration, and those spikes that you see starts very quickly vibrating, creating a locomotion. Idea is that you have seen those actually toothbrush with the motor. If you put it on the ground and basically let it run, it starts moving on the surface, right? So we made it like this. Now it can actually move across any basically different geometry against the gravity and everything. And we attach the camera into it, so you can see it very nicely with a very simple inflation deflation mechanism. We simulated everything and published in Science Advances. So now I'm thinking actually we can use something like this, which is tethered for colonoscopy, very small rather than a giant tube. So we are modifying it to do this. So I have a clinical collaborator in MD Anderson. Sorry if you're sensitive. This is a real surgery, and this is basically part of the body for gastric. This patient has, unfortunately, gastric cancer. They were doing the last step of the procedure. If radiation therapy, chemotherapy doesn't work, they excise the tissue. So this is over there, and I said, let's test. Let's build them something simple they can use in operating room as an edge device and test our sensor. I'm claiming I can use it for real patients, but is it really working on like basically tissue? So we made this handheld device for them, and so far we have collected, that's 34, but we're now testing it in MD Anderson. We have over 40 patients, clinical data, preclinical data, showing actually with our sensor, we can detect a stiffness change, and we can see, actually distinguish between a cancerous polyp and normal polyp. There are some issues, actually bowel diseases, that the only thing changing is under the surface is the stiffness of the body. Normal colonoscopes actually is not working. So clinicians just guessing how would be the next step. Surgery or basically medication and other things. We are showing actually if we just touch it, clearly we can see the area of the change of the stiffness. So we did all of this. We have a sensor, we have a robot, and we have a basically clinical data. Now I want to have an AI framework. As you know, for AI frameworks, they are data hungry. You need a lot of data to basically train your networks. It's a new sensor, no one has it. And we have just 40 patients, how to do it. So we started doing basically synthetic data generation or data generation with the robot. Started with the lab engineering way of doing it, attaching it to a robot. Let's just robotize the procedure, collect data. Well, that's not enough. Patients are different. It's very hard. So then we said, what if we use generative models? So to create synthetic data, I have some real data, some collected data, and we use different techniques. One of them I just want to talk about is relatively our latest technique is basic class condition latent diffusion models. Look at here, these are real images. These are what we synthetically generated. So in this case, we have some models. We train basically these machine learning algorithms, diffusion models, and synthetically generate a lot of data. But the challenge is, clinician comes in and say, okay, how do you guarantee these images match the property or like physical understanding of a real medical image? This is not a picture of cat or dog or like a car into the street. This has, every pixel has a meaning. So what we did here, we are doing basically in the latent space PCA analysis. And what you see here, basically the brighter points are synthetic data, the darker one is a real one. We are showing if you do the PCA analysis, they are matching actually. These are 4 types of polyps. And then we are using other algorithms helping clinicians with, oh, look at here, there is something, do you want to do anything or not? Then the next question is that you have a classifier, you have created synthetic data, you validated that. But how are you going to add it to your real data? Because the way you're adding data to your network makes it biased. So it's not like that, oh, I have tons of data, I'm going to add this to my network and train it. The issue is that some types of cancers, you see it more depending on the region, some types are less. So if I get like a public data in Europe for colorectal cancer and test it in Texas, it's not going to work. Because depending on their race, gender, and then food habit and other things, some types are more than the other one. In this case, you need to fill the gap. And how to add that data, we are showing here some like 4 methods that actually is good. Random addition, proportional addition, inverse addition, meaning that one group has less. Let me add more to that to be everything equalized. But you're showing here, actually, depending on how we are adding, the result is very different. The variation is very different. And this is a new research area, is bias in even AI and synthetic data generation. So the problem is already hard. You don't want to create synthetic data and then make it even harder for bad decisions. So then what we did, this is our basically, we just submitted this to ICRA. So we made this our setup. I said, I want to make it practical. So we got this basically NVIDIA Jetson Nano. Now we are running, I have my hardware to robotize this Jetson Nano, and AI is running on it, robot is running, everything is in ROS. And we made that AI system. So now we can start doing cool things. So test basically autonomous diagnosis with a user basically diagnosis, doing all test different AI algorithms because we make our own phantom as well. So this is basically just happened. Now we can test the whole system altogether. I know how much time I have. I can talk about this very quickly, like 4 minutes. Okay. Sure. I'll wrap it up. I promise you, this is shorter. So the third project that we started, as I said, my sci-fi project is in vivo bioprinting with volumetric muscle loss. What is that? If you have injuries to your body, to your muscles, if it's more than some basically size or range, body cannot heal itself. So in this case, we can use different techniques, surgery or like basically as a mechanical device, orthosis, basically devices, robotic device. Another method, which I had zero clue 3 years ago about, was tissue engineering, biomaterials. They make basically these cells and tissues called bioink that can push the body to regrow itself. So, but what they are using very archaic techniques, handheld devices to deliver things, or they are using some 3D printers like our normal 3D printers, print a delicate device and try to implant it. Of course, it's very challenging. And I said, what if we just do in vivo robotic bioprinting? I have a robot, I have a very nice imaging system, I image it, autonomously, precisely deliver it, and basically do that. Suggested this, and I realized actually it's a very challenging project. So we started building, basically attaching that RGBD camera, super precise, for imaging, and I started looking into, if I deliver something, I want to be very precise. I want to measure, quantify the quality of printing. So we started with these things. And then we made a handheld device. So in parallel, I have collaborators in LA. They are making bioink. So we need to develop this together. It's not like that I'm in Austin do work for myself, because it's an interdisciplinary problem. The material they are making should be injectable, should be cured over time very nicely. And then I need to know these design constraints while I'm making my robotic system. So we made this. Here we published this. Actually, they're showing those green things are real cells that growing over time. And that's the whole point. We want to print them. We want to make sure they're connecting to each other to replicate the fibers into the muscle. So then what we did, we made our basically device a little bit more complex and interesting. We are using a dual material, in this case, multi-layer, multi-material printing. We are using these chaotic nozzles, which is pretty cool. It's like we are using fluid dynamic turbulent actually concept to completely mix two materials together, because one of them in reality has cells, the other one doesn't have. You want to make sure like equally they are distributed. So we are buying this, we made this. We are just basically printing this under basically guidance of the robot. And then another very nice topic in additive manufacturing is closed loop bioprinting, or like additive manufacturing. Whatever we have, all the devices are open loop. You pass the CAD device, pray to the gods that the printer doesn't fail. You don't go there and then restart again. So here what we are doing actually real-time measurement with the camera, tuning the pressure and delivery speed of our robot to make sure everything is perfect, even for materials that curing over time. Because if they are curing, the viscosity is changing, so I need to tune or adjust my pressure. So here, basically, we are showing, even if the material is changing over time, I'm changing the pressure is regulated as we go to make sure that we are delivering the thing. Promise you last slide. So now I said we want to make an autonomous system. So we made this, molded this like giant Lexus, actually, Phantom here with different incision. 4-step procedure. Robot goes in, goes around the basically injury site, take pictures. That pictures goes here. We do a step 2 planning. Clinician goes there, like says, if you have a pre-planned trajectory, I want this point be here, this point be here, we register it. And then the robot goes in like very basically slowly, nicely. So planning is in 2D. We morph it to the trajectory that you have, and then robot executes, and then in the end, we do the basically evaluation. So last slide, of course, thanks my students. They are doing the real thing. I just tell them what to do. Sometimes they tell me what to do. And then collaborators and, of course, funding agencies. And thanks to you, of course, for listening. Appreciate it.
Okay, we have time for a few questions right now. Any questions from the audience?
Sure.
I just have a question on that last project. I guess what I remember from biomechanics is that like this matrix development is super important.
ECM, yes, yes.
Scar tissue. So I guess how are you all thinking about
Sure.
that? Or is this
So,
like the first step?
So this is literally last week my student actually resolved that. If you have a generic, you see here, first step we are basically measuring everything. We get the wound geometry because the challenge is that before the surgery, surgeons have some ideas of the injury site, but as soon as they start, they may change or increase the wound size for the surgery, for the connections. So we do this imaging, and we have now an algorithm. We have a specific ECM structure that we can adapt it to that, and then go very nicely plan. And that would be the next step. We command to the robot and goes there and do it. Basically, now we have a multi-material printing. The planning over there, we just need to execute it. But yes, that's ECM structure. They love it to have multi-layer and doing it.
Any other questions? Yeah. Any other questions from?
Yes.
So you're back ways a bit. You talked about the PCA that you did with the sensor.
Yes. Yes.
What were the features that you included in the PCA?
Sure. Yeah, the machine learning aspect. Yes. Let me show you. So pretty much what we are seeing here, we have an RGB image. What we are interested here, it goes to the network, and the network basically is a basically trained transformer. It goes to the multiple layers of a trained basically classifier, in this case transformer, and then we go and then run a PCA on the basically 2-dimensional last layer of transformer that understands basically based on the underlying layer why this is type 1, why this is type 2, type 3, and type 4. But what is this basically coming to this image for training is just the pixel level. But what is actually nice here, if you see on the type of pictures we generate, which is cool with this sensor, it's a 2D image, but because of lighting changes of LEDs we are using over there, it creates a sense of 3D and depth, as you see here. And those lighting helps us not only just say this is texture, a stiffness also changes with that, lighting changes. Because it's, if you have a harder objects interacting with the deformable layer, it deforms more the gel layer. So the gel is closer to the lighting source. So the distribution is different. So just by looking at an RGB image, you can have an understanding of the stiffness as well.
Thank you.
Yeah, I actually also have a follow-up question on that. So in this case, how is it, so I know that in colon cancer, it's really difficult to screen these like regions of interest, right?
Yes.
So all of these data were taken already around the lesion.
Sure, yes, yes. So, yes,
How
very,
is it different from the...
very good question. Because that's the whole idea of using a balloon, first of all. You are right. So basically, there are two modes you can use it, clinicians can use it. One is that they use a normal forward view camera and they see something suspicious. They can go over there, inflate the balloon over there to see some texture view, one. Second one, you say, I want to screen the whole colon. I don't know where it is. You go in and inflate, deflate, inflate, deflate, so you have a full map of the colon. In this case, what you are having, you have a normal RGB view and you have a tactile view, and you basically can get what you want. And we are running an AI on a normal, basically endoscope view, and other AI on a texture view. Now you can fuse them. One of them is saying 70% I see something here. The other one is that. So now you have two information in parallel that helps with decision making, unnecessary biopsy, and so on and so forth.
So what's the rate of false alarm? What's the rate of false alarm?
So force that we are interacting. So very, very good question. If I have the data here, yes, here I should have it. So you see on top, we have very tiny, we have a pressure we are having over the interaction force. These are two constraints because there is a regulation with FDA. You cannot go more than, I guess, 8 kilopascal and then 15 or 8, and then the force is 7 Newton. So we needed to make it that sensitive, within that range, even half of that. And if you see it, all those numbers are by far less than regulated things because you cannot push a lot, you're right. You may damage actually the anatomy.
Interesting.
Yeah, thank you. Yes.
I have a stupid question.
No
Why
question.
do you need the inflation and deflation to feel the texture? Like if you just need the tool and to feel the texture and transfer the data to the computer, it's just like.
So why we are deflating it basically? So if it's always inflated, the colon geometry is like this, tortuous, you cannot move inside. So you're breaking the balloon. So you had to move it. And another reason is that I talk to many clinicians, they don't want to always use it. They just want to use it when necessary. So you deflate it so it can easily move because colonoscopy is a very hard task. Navigation into the colonoscope is super hard because they don't see the body of the scope. So the scope is flexible. The anatomy is flexible. They don't see the anatomy, just see the front view. And there are a lot of sensors just built to put it as a skin on top of colonoscope to not damage even the tissue. Help them with this. So, and we are adding another thing on top. If you're always inflated, so it's already hard. So, sure. Yes.
So I've played around before with like very similar, kind of the more basic of these kind of gel tactile sensors.
Sure.
And from my understanding, so they use the red, green, and blue lights
Yes,
to
yes.
kind of, get some additional
RGB,
depth
yes.
information. So in your guys' case, so I'm trying to picture inside of this balloon, which way do the RGB lights face?
Sure.
Is there only one section of the balloon that can have
Very nice and technical question. So my poor PhD student, literally 12 months. So when we made the whole actually fully covered sensor, when we make this discrete one, it's a very nice question. If it's discrete, this part is transparent. If you have a light which intensity is high, it's going to escape through the sensor. But what you are having a fully covered, there is no escape of light. It's going to keep reflecting around, basically affecting on the quality. It's one of the issues that we have not in this generation, another generation that we have. This is actually, he's using one camera. We have 3 cameras. He actually, the whole summer, he's working on what's the best angle, what's the best intensity of the light, how to control it. Because if it's high, if you're lower, you're reflecting, and the quality drops. So we finally basically deepened into the distance is important, the intensity is important, and they have actually, Dr. Yuan, they have a software, and then Meta has a software. Basically, you can actually simulate its physics space, which is very nice. You can simulate the whole reflection and everything. But that's for the normal sensor, not for this one. But it's very, very challenging, yeah. It took him 2 years to make the sensor.
That's your tactile sense then, the pressure is based on the image.
Yes.
Not a pressure sensor.
Yes, so that's another nice thing. So as you inflate more, so what happens by inflation, you're making the structure more rigid. So the more rigid you are, the better. But you are inflating more. But there's another constraint. Colon is not that big. So you have a limited maximum distance that you can inflate. And there is a distance between the camera to the touching part too. So it's the focal distance of the camera becomes very important. The lighting condition becomes very important. And there are other aspects, so you cannot inflate a lot. And if it's very soft, so it's like a two spring on top of each other. So you are touching, but that deformation doesn't go to the camera, so you're losing sensitivity, basically. So industrial application is typically much easier because there is no limitation you push on it. Here, we had to make it very small because you don't want to make it big, so you cannot put it inside the body. Pressure is limited, sensitivity is limited. That's why I say poor PhD student. It took literally 3 years to make it to work. Even making that balloon symmetric, 1 year. Because once you make a mold, if one layer is like 0.1 millimeter thicker than the other one, what happens? You inflate. This part is thicker. This part is basically flexible. So you get something like this. You are not having a uniform deformation. It's just one PhD student making this sensor 6 years. Yeah.
I was just wondering, because this is pretty soft material,
Sure.
and what you're touching right there is all the material that you're touching it with is very hard.
Yes.
When you're inside the colon, the whatever thing
Polyp.
you get, it's probably going to, polyps are going to be much softer than this.
So it depends on the stage of cancer.
Yeah.
So stage 0, if we basically a patient would be lucky at that step we get it, and that's why we did that clinical basically testing. We have done it on animal tissues and other things to be.
Does the texture change if it's different?
Yes,
stages,
because-
or is it detectable? Is
So-
that this?
As it gets harder, so it creates more deformation on the gel layer, so the image quality becomes better. Because what happens is flexible. I said, the way it works, you have a camera. If it deforms more, you see more deformation in the images like this, you see here.
That could also depend on the size, but the texture would be a little bit finer.
Yes,
on the
very-
surface.
yeah,
It's
yeah.
difficult to-
Yes, that's what we tested and quantified our sensor on sandpapers. I didn't talk about it, but if you go back here, I'm going reverse, I guess. Give me a second. Yes, we wanted to quantify what's the minimum texture we can do. So we use sandpaper. Every sandpaper has a grit number, meaning that what is the resolution or the size of those grains. We could quantify it actually up